to be equal to, we know that F parallel is equal, sorry, I'm pressing this button by accident, and it's stuck. What is it? There we go. Is equal to F dot U times what?
Times
U. This is called the what? What is that?
That's a dot product.
That's a dot product right there. Dot product is a what kind of number? Is a scalar. And this right here is a vector. Nice. So this is the magnitude we want, and U is the direction we want to go in. Nice. Okay. So what do you want to find first?
Unit.
The unit vector? Nice. So U is a unit vector in what direction? The V direction, right? So what do we need to do? We need to take V and divide it by what? The magnitude of V. You with me so far? Well, we know what V is. What is V? Yeah, it's 5I minus J. Nice. What's the magnitude of V? The square root of what? 26. So we have 5I minus J. So that right there is a unit vector in the direction we want to go in. You with me so far? Okay, so we found the first part here. We found U. Yay. So now what do we need to do? Find the dot product, exactly. So we have F here. What's another way to, so now we need to find F dot U, correct? What is F going to be? F is 0I minus what? 20J. That right there is F, and we're dotting it times what? Well, dotting it, what's U? 1 over the square root of 26, so 5I minus J, like this. But what's on the outside? Does it matter when we multiply in the 1 over 26? The 1 over root 26? No, it doesn't. It's just a scalar on the outside. So when we do the dot product of these two things, we multiply the corresponding what? Coefficients, thank you. So what is this going to be equal to? What's the I going to be? It's still going to be 0I times the square root, 1 over the square root of 26. So what's the first term going to be on this? 0. I'm just saying, I'm sorry. You're right. It is going to be J. That's a proper answer. Correct. But I'm just putting it in there as a placeholder. So 0I, right? And then what do we have here? We have negative 20 times negative 1. So it's going to be plus what? What is it? 20 over what? J. Correct. 20 over root 26, J. Nice. So, oh, excuse me. This is a dot product. Why are you letting me write this in here? Sorry. So, the answer to this is going to be 20 over what? 20 over root 26? Are you with me so far? So that right there is the magnitude of the vector we want. But is that a vector? No. We need to put it in a direction. Do we have the direction? Yeah, what is the direction? There's your direction right there. So what do? This is your direction. And what's the magnitude of this direction? What's the magnitude of this direction right here? No, it's not. What's the magnitude of this direction? This was a what vector? This is a unit vector, right? So the magnitude there is 1. Sorry, there's a little hat right here. So what are we doing? We're taking this 1 over root 26, 5I minus J, and what are we multiplying it by? 20 over what? Root 26. Because that's the magnitude we want. So does something kind of nice happen? What cleans up a little bit? What do you end up with? 10 over 13 times 5I minus J, like this. Could you leave it like that if you wanted to? Sure. Absolutely, you could leave it like that. Could you multiply in the 10 over 13? Sure. You have to remember this, though, right here. F parallel, F dot U, U. And this is a C. Yeah, the speed of the current is going to be equal to the magnitude of what? Of C, correct. So what's that going to be? The square root of? 5. So it's going to be square root of? 5. So the speed of the current is root 5 meters per second. Are we okay with that? Doesn't give us a direction way of speed, but that's the speed of the current. Nice. It's that same thing we drew yesterday. Here is the Canoes Motion, okay? You can think of that as the velocity. And this right here is the what? Current. What are we trying to find? So if this is the current right here in green, what do we want to actually find? The component that's going in the direction of what? In the direction of v, right? But it's not asking, it says what is the speed of the current. So it's asking just for the magnitude of that, right? It's not asking for the direction, right? So basically it's asking for the magnitude of what? What are we going to call this? C parallel? The magnitude of C parallel. Now do you remember how to find that? How are you going to do it? There's two different, just so people can maybe get the trig first. So what was the first thing you said? It was going to be the magnitude of C.
Magnitude of C times the magnitude of V times cosine beta, which is the angle between.
Cosine what? Cosine, we're going to, like, oh, let me put a beta in there. Let me put something in there first so you can actually have something. That's beta right there.
Yeah.
There's one thing that you have to be really careful about. That's not actually, is it magnitude of V? Of the unit vector in the, I'm just saying that's really, really, really important. You have to be very careful about this, right? Because that's not true. It would be, we need to say like this is the unit vector that's going in the direction of V. So let me just change this right here. Like that. Are you with me so far? Yay? You are? Good. So, but what does that equal right there? What does this equal? That equals what? C dot what? U. C dot U. You see what I mean here? You can't just dot it times V because it's going to start, it's like this direction, right, doesn't change the component of this vector. Sorry, this magnitude doesn't change, like if V was 1 billion miles per hour, right, it doesn't change the component of C in the V direction. You need to make sure that that's a what vector? A unit vector. And they kind of started you in that by doing part A. Because what do you have to turn V into? You have to turn V, so it's going to be vector V divided by what? Oh, I'm doing double lines for some reason. Divided by what? How do you turn V into a unit vector?
You divide V by the magnitude.
Of V, right? Because this right here is U. Do you see what I'm saying, everybody? U is the unit vector in the V direction, so you need to divide V by its magnitude, which they asked you to do in part A. So what do we have here? We basically have, we have 1 over the square root of 5 times C dot V. Is everybody kind of with me on this? I'm sorry, what? Now what do we have to do? We do 1 over root 34 times the dot product of the two. What was C? C was I plus 2j. So what's the dot? We can just look at this and find out what the dot product is going to be, right? What is it going to be? 1 times 5 plus 5 plus 6 is what? 11. Okay. So this is what? Root what? 11. So, oh, it's not a root. What am I doing? Man, I just like putting in square roots today, apparently. So what do we end up with? 11 over what? Root 34. Does that kind of make sense, everybody? Kind of, maybe, sort of? A little bit? Let's just do product of two vectors is a scalar. The dot product of two vectors is a scalar. When we talk about the cross product, this is a vector. The cross product of two vectors is a vector. Dot product, scalar, cross product is a vector. This is important, and this is equals, sorry, is a vector. This is super important. As Umi pointed out last class, it is kind of annoying notationally because what is going to be the notation for cross product? An X symbol, right? Yay, nice. I also had a book once that instead of putting hats on top of vectors, it would just bold the letter. So it'd be like, this is a vector because it's bold. You're like, that doesn't help me. I don't like you, math book. Okay.
The physics books do, not necessarily with like the eyes.
Yeah.
Stuff, but for the
They bold
other-
stuff?
Yeah.
Yeah, I know. I just like, no, you can't use font changes. That's, no. Okay, so let's talk about this parallelogram right here. We have two vectors. Let's say it's nicely in one plane. We have a vector W, we have a vector V. How do you go about finding the area of a parallelogram in geometry? Do you remember how you find the area of a parallelogram? It's base times height, right? It's actually kind of cool when you think about it. You can take this this top and like slide it arbitrarily over, and it gets skinnier and skinnier, what happens to the overall area of this parallelogram? It stays the same. I don't know if you remember doing this, but one way that you could you can figure that out is if you're in this particular configuration, it's a nice configuration, but like if you chop that triangle off and then you plug it over, what do you get? You get a rectangle, right? You can always kind of construct that rectangle. So what's the height? What's the height of that parallelogram? Well, the height of that parallelogram is right there. There's your height. And here's your base. So what's the area going to be? The magnitude of V, right, times the magnitude of W sine theta. Now, that right there is the geometric definition of the area of a parallelogram. If we have the magnitudes and the angle between, we're good to go. If we have the vectors in component form, can we find the angle between any two vectors? Sure. So theoretically, if we have the vectors in component form, can we use that formula theoretically? Theoretically, we can. Is finding the angle measure a clean process? Not really. It doesn't always work out that nicely. But there's usually another side to all of these things, right? On the other side of the geometric definition for dot product, what was on the other side? The algebraic definition. This is what's really, really, really cool about this. Let me get to the statement right here. The area of this parallelogram is actually this right here. I'm going to cut this and put it up top. Two things that are really nice. It's in the x direction, and it's in 2 dimensions. Are we always going to be going in the x direction like this? No. Are we always going to be in two dimensions? No. But the first thing I want to tell you is, regardless of what direction V is going in, and regardless of what direction W is going in, this will always work in 2 dimensions. This will always work in 2 dimensions. It's really, really, really cool. W1 minus W2 minus V2 times W1. So remember what I said at the beginning of this segment. I'm going to show you some of this and give you the end product. What if we glossed over? What if we glossed over the relationship between? Where does this come from, right? Where does this come from? Because the general proof in 2 dimensions, and we're starting with 2 dimensions, has to be, this is not necessarily going to be on the x-axis. This parallelogram could be turned a little bit, right? In order to understand where this comes from, you need to look at this problem right here. It's a later problem from the book, right here. So here are the 2 vectors that could be used to make a parallelogram. So what would the parallelogram look like? You take R, place it right here, and you get the parallelogram. Do you understand the picture I'm drawing right there? Now, they start you off and tell you the key to determining the formula that they gave you above, which is this. Use the identity of sine beta minus alpha is equal to sine beta minus alpha is this thing right here. You all remembered your difference of angles, sine and cosine formulas, right? They're just memorized in your head. It's okay, you can say no. I did not memorize this. But it gives you the starting point. It gives you the starting point. The other key thing you have to remember, I was looking at this going, wait, where do I use sine? Well, what's the area of a triangle if you have the side length and the internal angle? Do you remember? If you have the side lengths, 2 side lengths and the internal angle of a triangle, what's the area of that triangle equal to? Do you remember? Oh, come on, geometry? It's 1/2 AB sine theta. Do you remember that? Do you remember that? Do you remember that? Does that vaguely ring any bells in there? So I'm going to give you both of the things you need to do this problem, part A right here, which is the area of a triangle is 1/2 AB sine C. If you have AB and angle C right there, that's the area of that triangle. Well, what's the relationship between this triangle and the parallelogram that the 2 vectors form? What's the relationship between this triangle area and the parallelogram's area? It's half of it, right? So what's the area of a parallelogram using this formula? AB sine C. Oh, there's your angle right there. So that's why they give you this thing right here. So part of your homework tonight, in addition to what's listed, I want you to answer this question. It's just algebra that you need to keep track of. It's just algebra. Be careful, be careful, be careful. The 2 things I want to point out, do you see the notation right here? It says B is equal to B1I plus B2J. So what does B1 equal to? S cosine beta. What do they not put around this S here? S is not a vector. What is S equal to right here? S is the what? This is the S vector, right? This is the S vector, and this is the R vector, right? You with me so far? So that represents a magnitude right there. That's the length right there, everybody. That's the length. So just be careful. You could put double bars around. It helped me. I needed to put double bars around to remember that it was a magnitude. But just remember, the area of a triangle is 1/2 AB sine C. So the area of a parallelogram is AB sine C. Use this, and you can prove the formula. But the key thing I want you to understand right now is that the formula exists, and that's what it is. The formula exists, and that's what it is for 2 dimensions. Now, you might be asking yourself, great, we're not just in 2 dimensions. How terrible does this get when we move to 3 dimensions? Not that bad when you understand how to keep track of all of these subscripts. This is the thing that's going to be the most annoying, like V1, V2, V2, V, like, what, where, how do I keep track of them? And that's what I'm going to give you. Again, I'm showing you the beginning and the end, and we're going to fill in the middle as we go. We're in 3 space now, everybody. We're in 3 space. I have a vector, let's say V, going off in that direction, and I have a vector W going off in that direction. I'll make it a little smaller so the scale makes sense. Going off in this direction. Again, I'm in 3 dimensions. Where does the cross product point? Where's the cross product going to point? The cross product points in the direction that is perpendicular to both of them. So this vector right here, the cross product is going to go like this because this vector right there is perpendicular to both of those vectors, here and here. Do you see what I'm trying to draw right there? Now this vector right here, this cross product, that's the cross product V cross W. And what's the magnitude of that vector going to be equal to? Do you see this area right here? That's the parallelogram formed by V and W. The magnitude of this cross product right here, the magnitude of this vector, the length of this vector is going to be equal to the area of that parallelogram. Do we have a quick way to find the area of a parallelogram now? In 2 dimensions we do, and I'm going to show you what it is in 3. But if you find this, and you have this, this is the definition of cross product. So, again, the dot product is a what? What kind of value do you get? A scalar. When you do the cross product, you get a vector. So if you have this vector and this vector, and you find the cross product, which I haven't taught you how to do yet, what do you get? You get a vector that is perpendicular to both, whose magnitude is equal to the area of the parallelogram formed by the 2 base vectors. Are you okay with that information so far? We haven't done anything with it yet. So the direction V cross W is given by a normal vector to the plane defined by V and W. If we require n, this is cool, if we require n to be a unit vector, there are 2 choices for n, pointing up and pointing down. Because look at this picture right here. What direction could I be going in? You could be going down. And what were you doing right there? Were you doing, you know the right-hand rule? Okay, good. Some of you, how many people have heard the right-hand rule before? Okay, here's the basic idea. V cross W is going to go up. Because if I put my right hand where V is, and I curl it to W, what direction is my thumb pointing? Up. If I do W cross V, you put your hand on W and you cross it to V, where's your thumb pointing? Down. You always curl to the vector you're crossing with. So, ready? V cross W, up. W cross V going down. Say down, okay? So, does the order you cross in matter? Yes, it's going to give you 2 vectors. If you're just searching for a perpendicular vector, this vector is perpendicular to this plane. What about the vector going straight down? It's also. So if you're just searching for a perpendicular vector, do you care? No. But are they going to be different vectors? Yes, they're going to be going in opposite directions. They're going to be going in opposite directions. So here we go. This is the last piece for right here. This right here seems simple enough to try to remember how to find really easily. I'm going to just memorize flat out, I'm going to give you the methodology which can be expanded to 3 dimensions. You take your components V1 and V2, W1 and W2. Has anybody worked with matrices before? Maybe, yeah. It's a hit or miss type of thing. If I ask you for the determinant, and I'm not telling you what that is right now, but the determinant of this vector, you get to do this a lot when you take linear algebra, which is something almost all of you are going to take. You do these two multiplied together, so what does that equal? V1, W2, and you subtract these two. V2, W1. Oh, look what we have up there. Does everybody see that up there? You see that crossing? You do, this is a 2 by 2 determinant. This product minus this product. This is the basic unit for finding determinants. You can find the determinant of any square matrix. What's a square matrix?
Even rows and columns.
Same number of rows and columns.
Yeah.
Same number. Yeah, they're this equal number of rows and columns. You can find the determinant of any square matrix. You use this to find inverse of matrices. But this minus this. But you're like, wait a minute, Mr. Seamon, this doesn't really help me because we need to do 3 dimensions. This is the shortcut that I am allowing you to use so that you don't have to remember that big kind of complicated thing that does not seem to be helpful or anything you want to have to spend time totally memorizing. Because what happens if you get one of the variables wrong in the wrong place? Boom! Number don't make sense no more. Okay? Ready? This is what you do. If you have two vectors, v is going to be equal to v1i plus v2j plus, not w, Mr. Seamon, plus v3k, and w vector is equal to w1i plus w2j plus w3k. What two vectors could those represent? Any two vectors. You with me so far? Any two vectors in 3 space? We're finding the cross product, which is a vector. This is what it equals, everybody. And notationally, this is what it looks like. V cross W is going to be equal to what you first do top, then you write V, V1, V2, V3, and then you write W, W1, W2, W3. We are going to, I'm teaching you now how to do a 3 by 3 determinant. There's a process to it which is a lot easier to memorize than all of those numbers in order. So what you do first is you say, I want to find the ith entry. So what you do is you eliminate the row and the column that I is in. What are you left with right there? What's this? How many, what kind of matrix is that? 2 by 2. That's a 2 by 2 matrix. You with me so far? Can you tell me what the determinant of that 2 by 2 matrix is? V2W3 minus V3W2, and that's the ith term. Guess what you do next? Take a guess what you do next. You want to do the J once you cross these out, right? What's the thing that's left? V1W3 minus what? V3W1, and what does that get multiplied by? J. You with me so far? So then let's do the last one right here. It's a repetitive process. This one you nuke those, right? I'll write it down below. This is going to be V1W2 minus what? I'm putting the V's before W's just as a standard alphabetical order maneuver. And what goes after this? And it's K. Correct? So where does this go? Where do I put this if I'm writing this properly? I take this, and what do I do with it? I take it and I put it right here. And this is the last piece that I can guarantee you're going to forget sometimes. It goes plus, minus, plus. Plus, minus, plus. So what do you put in between here? Minus and plus. Guess what that is equal to right now? Look up here. Or where, oh, did I put it in the wrong space? I did. Where did I put it? Take a look at down here. What is this right here? Let's see how we did. I'm curious if we did it correctly, because is it really, really easy to do these wrong? The cross product. What is the relationship between this vector and u and v? What's the relationship? It's perpendicular, right? To both of the vectors u and v. And its magnitude is equal to the area of the parallelogram formed by u and v. How do you find out if two vectors are perpendicular? Dot product is what? So this, we started with any two three-dimensional vectors, and what did we do? We took the cross product. which I'm telling you is supposed to be perpendicular to both of them, right? Could you actually algebraically test that? You could take this vector right here, and what could you dot it with?
One of the other.
Either one, and it should come out to be in both instances. Could you do that? And that would then prove what I'm telling you. The biggest thing you need to walk away with right now is this picture right here. See this picture right here? How are you with this method that I just gave you? How are you feeling about this method right now? Decent-ish? You can practice it a little bit. You'll get better at it. Keep in mind, the second thing, in addition to the written homework, what I want you to focus on, go back. It would behoove you, it would be useful to understand this question right here. Do this. It's not that bad. It's not that bad. Just be careful with the notation.